Okay, the last couple of problems on the sheet were incorrectly numbered 10 and 12. I might have corrected my copy here already. There's just two more, 10 and 11. So we've got a graph that shows the temperature in degrees of Robert's cup of coffee, t minutes after pouring it out. And obviously because it's cooling down after he's poured it out, we can see that this is an exponential decay function. The equation of the cooling graph is 16 plus 74 times 2.8 to the power of negative 0.2t. Sorry about the formatting there. And f of t, this function, represents the actual temperature at time t, where t is the number of minutes after pouring the coffee out. So let's find the initial temperature of the coffee. So initial, this word initial, means that time is equal to 0. Let's look what happens when the time is equal to 0. We are starting somewhere between 80 and 100. More specifically, yeah, it's so inconvenient, this info. I'm going to rewrite the function. I'm sorry about this. F of t equals 16 plus. Remember, if we add a constant onto a function, that means that we have moved it upwards by this amount, right? It's a vertical shift. So, and here's the exponential part, 74 times 2.8 to the power of negative 0.2t. Well, you remember that this is an exponential function because our variable is up in the exponent, and so this part is the power. I've got a base and a power, and the coefficient in front of this power represents our normal y-intercept. So usually our intercept would be at 74. However, the plus 16 means that we have moved upwards by an additional 16 units. 74 plus 16 gives us 90. Another way that you could argue this is, if t equals 0, why don't you just substitute t equals 0 into the function? And so our f of 0 is equal to 16 plus 74 times 2.8 to the power of negative 0.2 to the times 0. Now we could stick this into our calculator, I suppose, but I think that we could reason it out even quicker by realizing that 0 times anything is 0, so this entire exponent, is 0. 2.8 to the power of 0, just like anything to the power of 0, is equal to 1. 74 times 1 is 1, and 16 plus 74 is 90. So there's another way that you can get it, but I'll show you how to do it on the calculator anyway, just so that those of you who like the calculator can follow a method. 16 plus 74 times 2.8 raised to the power of negative 0.2t. And we get, I'm a little bit perplexed. Let me just think about this for a moment. I can't see a reason that this is happening. This is certainly... oh, I'm so silly. I forgot that, of course, x, I can't leave it as an x. It's a 0, isn't it? So let's bring up my previous entry. And I'm just going to change that last value to a 0. So times 0. Much better. There's the 90 I expected. And so the initial temperature of the coffee is 90. There must be a unit in degrees Celsius. Here it is. So degrees Celsius. Part B, write down the equation of the horizontal asymptote. Alright, in an earlier video I reminded you that in any exponential growth or decay function, your horizontal asymptote of a function is normally along the horizontal line whose equation is y equals 0 at the x-axis. And as I showed you already, this coefficient of 74 implies that our y-intercept would normally be at 74. But the plus 16 in the function demonstrates that we are moving this entire function upwards by 16 units. So our y-intercept became 90, as we discovered in part A, and our y-intercept will also move upwards by 16 units, and so the equation will be y equals 16. Another way you could have done this, which I've never shown you in class, but I think will be nice for you to see if you're watching this video, so congratulations for taking the time. You're going to like this, I think. I've just realized there's a really nice way to find the equation of an asymptote. If you have trouble with transformations and realizing that this 74 in front implies that we're starting at 74, or this plus 16 means we're moving upwards by 16, here's another way of thinking about an asymptote. We can see that we're going to get flatter and flatter and flatter and approach a horizontal line somewhere where t, the number of minutes, gets very large. So what we could do then is put in our function 16 plus 74 times 2.8 to the power of negative 0.2x. Oops, oh damn it. How many times that happened to you, right? Let's see, 16 plus 74 times 2.8 to the power of negative 0.2. Go on, show me. Negative 0.2 times, and that's all I got to, wasn't it? So let me just change the times into an x. That's going to be fine. Of course, that means multiplication. And now I'm going to look at the table. Now what I'm looking for is where the y values basically stop changing very much. So if I scroll down a lot, you see that my y values start getting closer and closer and closer and closer to 16. For that matter, if I changed my table set, so instead of me going up by ones, what if I was going up by, so I'll say, second window to go to my table set, what if I was instead starting at 40, but going up by increments of 10? Now let's have a look at our table. So you can see we're going 40, 50, 16, and look, I've basically gotten so close to 16 that the calculator can't distinguish between that value very close to 16 and the value 16 itself. So this is a nice way of finding asymptotes, is by looking at the table of your function as we go far into the future, or if it was an exponential growth function, in that case it would be far into the past as t is very negative, and determining when does your y value stop changing. In other words, when does it become so flat that it's basically the same as a horizontal line. And in this case it occurs with y equals 16. That's the equation of the horizontal asymptote. Any horizontal line is y equals. Part C, we need to find room temperature. Let's think about what's happening here. Robert poured out his cup of coffee. It was 90 degrees Celsius. Over time it began getting cooler and cooler and cooler. We can see its temperature declining as time goes forward. Now, if his temperature eventually flattened out at an asymptote of y equals 16, what does that mean? Well, it must mean that room temperature is 16 degrees, because his coffee is gradually going to cool to room temperature. It can't go below room temperature. If something cools, it always cools to the temperature of the surrounding area. So the room temperature must be 16 degrees Celsius. Part D, what's the temperature of the coffee after 10 minutes? So let's substitute in t equals 10. So our function, our temperature after 10 minutes, is 16 plus 74 times 2.8 to the power of negative 0.2 times 10. Now I've got this function entered in. The only thing that's different about it is that I have a 0. So why don't I call back that previous entry? I'll say second enter, and it brings up the equation I just typed in and allows me to edit it. I want to change my exponent to a 10, and it gives me a temperature of 25.439 if I give some extra decimal places, and so my temperature is, where am I going to write this? Equals approximately 877 if you want to be even more precise, and it goes on, but I'm just going to round to 3 significant figures, 25.4 degrees Celsius. And it goes on, it says if the coffee is not hot enough, it is reheated in a microwave oven. The liquid increases in temperature, so here comes our growth function now, according to this formula. So T is the final temperature of the liquid after it's heated. A was the initial temperature of the coffee in the microwave. So there's A, the initial temperature. T is the amount of time in minutes after we've switched the microwave on. Part E, find the temperature of Robert's coffee after being heated in the microwave for 30 seconds. Now let's remember that time is in minutes, so 30 seconds implies only 1/2 a minute. That means that T will equal 1/2 in this in this question. After it has reached the temperature in part D. So his coffee went all the way down to, in part D, after 10 minutes, it cooled down to 25.4 degrees Celsius. So that's the initial temperature of the coffee when he put it into the microwave. And it's been heated for 30 seconds. So in other words, our T is now equal to 25.4, our initial temperature of the coffee from part D, times 2 to the power of 1.5 times T, and our T, we agreed, is 1/2, because it's only being heated for half a minute. Alright, let me type this into the calculator then. I've got 25.4. In fact, I could be even more precise if I just called up the answer that I had a moment ago. I'll say second, gosh, I can't see it on this calculator. Oh, there it is, second negative. That calls up the answer that I just had, which is 25.4387 cents, super accurate. And then I could use that value and multiply it by 2 to the power of 1.5 times 1/2, which is 0.5. And it gives me that after 30 seconds the coffee is heated to 42.78275. And if you don't mind, I'm just going to round that immediately to 3 significant figures of 42.8 degrees Celsius. That's what it's heated to after 30 seconds in the microwave. I'm just trying to think whether there was something else I was going to say to you a moment ago. I had something in my mind. Well, if I can't remember it right now, then maybe it's not important. Part F. Let's calculate the length of time it would take a similar cup of coffee, initially at 20 degrees, to be heated in the microwave until it reaches a final temperature of 100 degrees. So T represents the final temperature, and so that's 100, if we finally got up to 100. Our initial temperature was 20 degrees, that's A. And so, yeah, there's A, the initial temperature, so that's 20. So 20 times 2 to the 1.5, and we're looking for T, the number of minutes, the length of time it takes for this to occur. Now, we might not expect a microwave to only heat things up at the end of each minute. It's gradually heating it up, including during part of a minute. And so a table is not a good approach here, because a table would only give us integer values. We might have a decimal value. So I'm going to use a graph. Say y equals, let me clear this old one. So I've got 100, there's my constant function of 100, the left-hand side. And my right-hand side is 20 times 2 to the power of 1.5. Oh. Ooh. Has my calculator crashed? No, there we go. 2 to the power of 1.5 t, or x in our case. Now, before I actually graph this, let's adjust the window. I know that my initial value of the coffee is 20, but it's going to be heating all the way up to 100. So I have to be able to see those values on the graph. So let's make my y max at least 100. I'm going to say 110. And my coffee starts off at 20 degrees, but I'm happy just seeing the x-axis by going a little bit below, maybe just -1. And in the x direction, let's think. Well, obviously I can't have negative time in the microwave, so it starts at -1, so I can see the y-axis, and I don't know how long it will take. I presume surely it should take a microwave less than 10 minutes to heat a cup of coffee up to boiling temperature. So let's see if we can see it here with a graph. There's our 100, our constant function, and there's the heating of the coffee. Wow, that is quick in a microwave. It looks like the answer is somewhere between 1 and 2 minutes. Let's find that intersection point. And whoops, if I'm showing my work here, I should really explain what's going on with a graph. So, Here's my constant function of y1 equals 100. Here's my quickly growing function of y2 is equal to 20 times 2 to the power of 1.5x. And this intersection point, which I'm about to find, occurs, so this is my first curve, 100. That's my second curve, the big exponential equation. And I want to guess, well, it looks to me like it happens somewhere between 1 and 2. So I'm going to say 1.5 is my guess. I could have moved the cursor there as well, but it's quicker just to type in the x value. It tells us that it occurs at 1.5479 blah blah blah, and so I can see then I should fill in my intersection point. I'll just do it to 3 significant figures, 1.55, and my y value is of course at that constant of 100. And so let's actually answer the question. The length of time, t, I can see is going to be 1.55 minutes. Always include units in a real-life problem. And the last question you've been assigned is number 11. A national lottery is offering prizes in a competition. The winner chooses either option 1, option 2, or option 3. Now option 1 says you get $1,000 each week for 10 weeks. That's pretty simple, isn't it? After 10 weeks, of course, you would have, just going to write this at the bottom. After 10 weeks, option 1 would give you $10,000, right? $1,000 each week for 10 weeks. Option 2 gives you $250 in the first week, $450 in the second week, $650 in the third week, increasing by $200 each week. Now we know that if we're going up by 200 every single time, that is an arithmetic sequence, and with a d value of positive 200. Furthermore, we can see that if 250 was the first week, that u1 is equal to 250. Alright, so we need to calculate the amount that we receive in the 10th week if we select option 2, which is the one that we were just looking at. We'll talk about option 3 later on. So let's kind of write this out as a arithmetic sequence. The amount that we would receive in the 10th week would be equal to our initial term, 250, that's our u1, plus, and we've been incrementing by $200 every single week. So in the second week, we had increased by only one $200. In the third week, we had now increased by two $100. And so this increase of $200 is always one smaller than the, whoops, maybe I should have written it as a 10 minus 1. 10 minus 1, because it's an arithmetic sequence, there's your n minus 1 times your common difference. Alright, let's just calculate this then. 250 plus 9 times 200 shows us that in week 10, in option 2, we would receive $2,050. Option 3 says that we get $10 in the first week. That doesn't sound like very much. 20 in the second week, 40 in the third week, and so on, continuing to double. This means, of course, that we're multiplying by 2 every time, and that implies it's a geometric sequence where the common ratio is 2, and we can see that our first term is equal to 10. So we know that in a geometric sequence, un is u1 times r to the power of n minus 1. In our case, u10 then is going to equal our first term, $10, which is multiplying by the common ratio of 2 to the power of 10 minus 1. So let's figure out what we get when we do 10 times 2 to the power of 9 minus 1 is 8. Oh, 10 minus 1, I'm sorry, is 9. And we got, wow, $5,120 in the 10th week. Forgot units. There we go. There we go. Alright, what is the total amount we receive if we use option 2? Option 2 is the one that was the arithmetic sequence, and we know that that's going to be then... now this is finally an opportunity for us to... so we're calculating option 2 here, aren't we? Finally an opportunity for us to use that other arithmetic sum formula, the sum of the first 10 terms. This time we do know our 10th and final term in the 10 weeks. So why don't we use the formula that was n over 2, in our case 10 over 2, times our first expression plus the last expression. You remember the one at u1 plus un? So So we've got our first amount, 250, plus our last amount, 2,050. You could also use the other formula because you do know what D is, and if you know what D is, using the other formula is fine. But if you know your last term already of the 10 that we're adding, well, why not use the simpler formula? And so that gives us then 10 over 2, which is multiplying the sum of 250 and 2,050, giving us an answer of 11,500 total dollars received for option 2. So option 2 is a little bit better than option 1, where we only received a total of 10,000. In option 2 we've got 11,500 as the total payment through 10 weeks. But part C says which option has the greatest total value? Maybe option 3 gives us even more money. Option 3, you'll remember, was a geometric sequence. So let's use the geometric sequence formula. And so that was Sn is u1 1 minus r to the n over 1 minus r. In our case, the sum of the first 10 terms is our initial term at $10. 1 minus r is 2 to the power of 10 all over 1 minus 2. And let's see what the sum of the first 10 terms is in option 3. Our first term times 1 minus 2 to the power of 10 divided by, I've done this earlier in this video, haven't I? Let's get rid of these and get out of the exponent to close the parentheses. And now we'll divide by the denominator, which has to be put in parentheses, 1 minus r, or 1 minus 2. And the total value paid is $10,230. So obviously, which of the 3 options has got the greatest total value? It's option 2. And we had to justify our answer by showing all calculations. But let's actually answer the question now. Option 2. And you can see all of our calculations. Well, I didn't really show my calculations for option 1, did I? So let me just rewrite that to make sure I get full credit. My $10,000 was multiplied by 10 to give me 10,000. And the 10,000 nor the option 3 total amount of 10,230 was as much as my best option to choose as the lottery winner, option 2. Alright, that concludes the review on exponential equations, arithmetic and geometric series. Good luck studying. See you later.